passes slowly, makes me feel lonely. Gotta stop feeling sorry. I can't always feel worried. Mine won't stop singing, and I keep on overthinking all the time. I hope with time the healer will mend my soul, and I can let you go. But I believe someday soon I'll learn to overcome it. The scars will heal, hope will bloom, no more dwelling. 'Cause today I choose to say I will love again someday. So I'm not gonna stay paralyzed, not by your side. But I believe that I will be much better eventually. But I won't forget our love ever. Time heals all. Know that time heals all. I believe that someday soon I'll remember you with a smile and overcome, and I will overcome. Someday soon I'll overcome. Someday soon I'll overcome. I choose to say I will love again someday, again someday. I'll was good to know you, but I'm not gonna pretend I'm all better. Thought we were forever, heart still in pieces, and your shadow follows me places all the time. I can't shake this feeling of loneliness. That's just life, I guess. But I believe someday soon I'll learn to overcome it. The scars will heal, hope will bloom, no more dwelling. 'Cause today I choose to say I will love again someday. So I'm not gonna stay paralyzed, 'cause I'm not by your side. Time passes slowly, makes me feel lonely. Gotta stop feeling sorry. I can't.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
All right, so today we are going to teach you something about performance, but in a different way. So you probably heard the song Sunday, and some of you might heard it, some of you might not. Let me tell you where it is from. I'm not sure how many of you ever watched this anime before, but if you haven't, it's one thing that I would recommend you to watch on Netflix. It's called Great Pretender. And it's a song that coupled with this animation series in one of the few episodes, and it's one of my favorite animation that I would say. And so in this animation, the main character is actually someone who is like a liar, a pretender that tries to deceive a lot of people. And today, I'm going to tell you how to become a liar, or on the more positive side, how to see through those lies, those alternative facts before behind those performance numbers. But before we start, let's recap where we are coming from. So we have been talking about CPU performance equation for a while. You're very familiar with this equation right now. You know, execution time is composed of three components: the instruction count, the CPI, and the cycle time. And through the lecture demos, you should know that programmers can control everything. And and the compiler programming language does affect performance, but only on instruction count and the CPI. And then we talk about, well, how do I know if I'm doing better? So that's, we want to define if something gets better. So that's called speed up. And there is only one definition in terms of speed up. That is the execution time of your baseline system, which we say is the X here, and over the execution time of Y, which is your improved system. So if you want to say the speed up of Y over X is defined by execution time of X over execution time Y. And then later in the lecture yesterday, we talked about another law, which also talk about speed up, but in a different format. That's MDOS law. However, the MDOS law is nothing different from the definition of the speed up that we just mentioned from the lecture. It's actually rescaling the execution time of your baseline to be 1, and we separate the total execution time into two pieces, F and 1 minus F. And F means the fraction of execution time that could be improved after applying certain optimization. And with that optimization being considered, the 1 minus F, which is the unaffected part, should remain the same. And for the remaining part that the optimization can speed up, should also receive the effect of F over S in its execution time. So if you apply the speed up equation, you will get exactly the format of MDOS law, which is 1 over 1 minus F plus F over S. So that's MDOS law. And that's where we are. And regarding our progress of getting Amazon gift cards, so far, our blue groups have some kind of, is a little bit falling behind, but and unfortunately, this is not MLB, so we cannot trade someone from somewhere. Otherwise, it's probably a good idea to trade someone from the yellow team, right? But I think you guys should be able to catch up. So hopefully today it's your show time. But before we start, as our tradition, as I told you, we do encourage you guys to have conversation with your group first. So to begin with, the first question I want to have you guys talking about, I want to have you guys asking around within your group is that, have you ever been misled by some commercial? In what way? So let's go ahead and start. I just found that I forgot to unmute myself. So can some of you share your thoughts with us? All right, Elliot, you are my friend.
Hi. So our group talked a lot about like drug commercials in the US, like for pharmaceuticals and stuff like that. We felt like sometimes they would depict like really, really happy people like as a result of them like buying this, new pharmaceutical thing, but it often felt like to us like it was just like you can't literally just like buy happiness from a drug, and like a lot of the time like at the very end of the commercial they'll like blast through all of the side effects like really, really quickly. So right, so
All
it
right.
feels kind of disingenuous. Yeah.
Okay. Although I'm a little bit surprised that like as as young as you guys, you start to pay attention to the drug commercials. So that's a little bit surprise to me. All right, David. Hopefully you guys are not using that too much. David.
I guess just like adding up to Elliot's comment, I guess also not only drugs, but you see a lot of like supplement commercials that like I guess they advertise like a lot of benefits of obscure like minerals or obscure like chemicals in their product, which their effect like may or may not like be placebo, but like they advertise it as like something is very beneficial to you.
Okay. What else? So they don't tell you the side effect. They only tell you the good thing. Vince.
Fast food commercials where like let's just say some like I don't know, Burger King. Like they'll make their burgers in the commercial look very colorful, very like fluffy and everything. But obviously when you go and get the food, it's not that visually pleasing.
So the quality of service, well, the quality
Yes.
of the result is not as good as when you actually buy it.
Yes.
Okay, what else? All right, so looks like those are some common things that we experience every day in our life. Like, okay, when you purchase something, they just don't tell you the bad parts of that, right? They only tell you the good thing. And or they just tell you, well, this could be this good, look like this good, right? If you do this, but they don't tell you that in general, it could be that, right? So those are the experience that you had in it before. And today, I just want to continue our discussion on MDOS law. And the other thing that I want to tell you is that how people would usually fool others with performance matrices. So, and I will show you some real examples, and you probably would have some kind of empathy, or well, what's the word? Empathy with that, right? All right. So last time we talked about, wait, am I getting the right one? Okay, so the last time we talked about speed up, but why am I having these slides here? Okay, so today we are going to continue our discussion on MDOS law. So we in the last lecture, we stopped at this question, right? None of the above, as if you remember what's going on in the last lecture, you should know that, well, I tried to apply MDOS law, but it tells me a stop that is less than 1. So it's not actually speed up, but I know if I want to make my performance better, I definitely want to get speed up. So this makes no sense, right? So which means that, well, even MDOS law is broken or the whole thing doesn't make sense. So the answer is the later. The whole thing doesn't make sense, right? So so another one way of seeing it is that, okay, so in Flash, right? When you use Flash memory, the hardware part is only account for, if the hardware part is only account for 16% of the time, right? Then how come it could be possible achieving 2 times speed up, right? So if you try to I would say tweak the MDOS law a little bit, you can actually found the maximum speed up by optimizing some part of the program. So for example, if the optimization I can apply can only take effect on this amount of time, then the maximum speed up that we can get is actually, the maximum speed up that you can get is unlimited, right? Which is the best ever speed up that you can get. So if you apply these 2 parameters into the speed up function, then it will end up give you that the maximum speed up is 1/1 minus f. So if you go back and look over this, right, 1/1 minus 16% actually give you 1.2 times speed up. So if you want to achieve twice speed up, that's impossible. That's impossible, right? So that's why I'm saying, if your boss is asking you to achieve twice speed up in this case, then he is actually, or she is actually, or they are actually asking you to leave, right? Because it's impossible, right? So it's a gentle way of saying that, hey, I don't think the company is for you, right? So two times speed up is not possible, right? So that's one thing we like about MDOSLO is that if you can clean up your performance into this form, then it's actually making you easy to figure out what's the maximum potential of optimization in your programs. So now, and one thing you can see, right? So recently, it's not too long ago, right? Just a few days ago, Intel announced that they are going to kill their last product line of Optane memory, which is a 3D cross-point memory that is supposed to be 10 times faster than Flash. And to be honest, the number that I cited in the previous question is indeed reflecting the real numbers when you're running applications. So given that, right, even though you have the Optane memory, which could be twice or 3 times more expensive than your flash memory, but you cannot get that amount of speed up with that. Who wants that, right? So the business model won't success in that way. So that's why they killed that. But in the very beginning, right, if they are smart enough, they should be able to apply the MDOSLO to figure out, it's not worth spending time on this product. All right, so another example that I could give you is that, well, you know, San Diego Padres before Tuesday, well, I think their GM did a very good analysis, right? So in terms of pitching, they are the best well, they are ranked number 8, but in terms of hitting, they are only ranked like number 18. So that's why if you look at, well, to improve, right, the room of improvement here is very minor. However, there is a huge potential of improving that, right? And if you say that both of them are equally important, definitely this side is important. So most of the trade are focusing on good hitters like Juan Soto, right? So that's a way of applying MDOSLO. No, I'm just talking about, I'm so excited about again yesterday. Anyway, all right. So now let's talk about our corollary one. So if you remember, right, MDOSLO can actually be applied on multiple optimizations. And if you find this F1, F2, F3, F4, they are all disjoint. Then with the format of estimating the speed up of a max, it actually tells you is that if you can only do one thing, what's that one thing we should pick, right? So it's simple, right? You just do you just apply the maximum speed up equation to all parts, and you will figure out whoever gives you the maximum speed up should be the one that you should focus on, right? So this one would give you the second corollary, which means that if you want to maximize your effort in making optimization, then the very first thing to do is to make the common case fast. And according to MDOSLO corollary 1, it's actually the most time-consuming part because look at this formula, right? Who would ever give you the best speed up would be the one with the largest F. So, and the F is the fraction of time that we could improve. So most time-consuming part is the common case that we should apply. We should apply optimizations on. And another myth is that people would typically think most time-consuming part would be the most frequent thing. However, that's not the case. Most frequently, code function could be relatively simple function that don't take a lot of time. So based on how many times calling the function is called, or how many times this pieces of code is being used, does not make the case of common case. So the only way that you can actually do this is that you have to use profiling tool to help you figure out who is the most time-consuming part. So let's look at this, right? So that's one thing that you should learn from MDOSLO as well, is that make a common case fast. And Another thing that I want to talk about is that, well, let's go back to this flash SSD stuff, right? So one thing that you will learn is that, well, sometimes, right, if you are using flash SSD, you can probably see that, well, hardware is still a significant portion of time. However, after apply PCM, the hardware becomes less significant. However, the operating system becomes more efficient. So optimization is always a moving target. When with optimization being applied, the common case becomes uncommon. So people typically have the stereotype of something must be the bottleneck of the program. However, the bottleneck could change over time. So it's always important that every time when I have a new system, when I have the program, I should try to identify the most time-consuming part in my program. So to do that, there is a simple way of doing that. That's actually when you compile your program, try to use the -pg flag. And it will, if you are in a Linux system, you can use profiling tool like gprof that would generate the timing breakdown of your applications. So right now, what I'm going to do is that I'm going to show you some simple demos regarding the breakdown of execution time in applications. So maybe I can just give you a very simple program to look over. So let's say we have this program, array sort.cpp, and let me do this -pg. All right, so let's make array sort. All right, so now when I run it, let me see what's the input of array sort. Okay, so array size, and I think I want this. All right, so if you run this program, oops, iterations, okay, 1000. All right, when I run this program, 10,000. When I run this program, right, it will, if you look at the outcome, it will generate this gmon.out, right? And remember what we have in the slide, just gprof your program, gprof your program was program binary with that gmon.out. It will generate a lot of outputs like this. And in Linux, if you want to aggregate this output into a file, the easy thing to do is that you can use this shell, this redirection in your shell to an output file. So for example, I can say it's output.profile. Then you will be able to see this output in your profile, right? And it tells you that, well, the calculate sum is actually the most time-consuming function, right? It has been called for 10,000 times. However, it takes about 1.34 seconds to finish, right? However, other functions like this one, iteration, less iteration, or like this remove reference function, or this unguarded linear insert, unguarded partition function, move median to first, they are used by the sorting function. Although the times of calling these functions are more frequent than just this 10,000 calls of this calculate sum. However, the amount of time we spend in calculate sum is a lot more than other functions. So that's why it's really important that if you look at this one, if you want to improve performance, figuring out how to improve calculate sum would be the key. All right, so that gives you an idea that how can I identify the most common case in my program. So another demo I want to give you is about a moving target. So this is and I can just run the the demo right now. So for this machine I have in particular is an NVIDIA machine that has the latest 3090 GPU. So it's definitely not a machine with mediocre GPUs. And this, oh well, I can tell you a lot about the story. How I get this GPU probably a year and a half ago, but it's not easy. If some of you were intensive gamer, you know how difficult is it to get this, right? So but today I'm here to use that for demo for you, so you know how I treat how well I treat you guys. So this is the GPU that we are going to use today, and we are going to use the GPU to show you how we can optimize the sorting function. So now so my baseline program is a CPU program that runs the quick sort. And if I just use well, let me check what's in the script. And okay, so today I'm going to use the CPU to sort 134 million numbers from this particular input file. So now let me run this program and let you see how much time it would take. So wow, shoot, okay. Okay, because our file system, if you learn operating system, you know that to optimize for performance, they would intensively use your DRAM to cache file data. So for this program to be fair, to make a fair comparison, which you know you will learn what is a fair comparison later, I try to clear the cache before we start the program. So it will be fair when I run each experiment, because everyone will start at the same condition. So right now I'm running the CPU version, which means that I'm using the CPU for computation. And the original input file would be coming from a solid state drive. Sorry, not a solid state drive, a hard disk drive. And let's see how much time. Wait, is it from a solid state drive? Let me check. Shit, what can I use this for? Okay, so let me check, let me change it actually. I don't want it to be from here. I have this file here. Not really. Okay. Then that will take a lot of time. All right, never mind. I thought I have that file here. All right, sorry for that. But well, now I'm loading the file from somewhere that is slow, which I regretted to do that. It's from a traditional hard disk drive, and the bandwidth of that traditional hard disk drive is actually 100 megabyte per second. So you could imagine that would take a lot of time when we try to load the file. And let me see. All right, I regret it. Let me use another machine to run the demo. All right, so this is another machine. It has an older GPU. So the GPU that has been used here is also not bad. It is an NVIDIA 2080, which is the previous generation of the NVIDIA GPU. And now I'm using this machine for the demo because I believe the hard disk drive on this machine is faster. And let me see if I can, do I have that here? Okay, here we go. All right, so let me see if I could use that. All right, so let's run the demo. And as you can imagine, because we are just using a CPU, so it may be a little bit slow. Yeah, we are using the CPU, right? Okay, so on this machine, right, because we have a faster hard disk drive, so to get the input file, it actually takes only 3.5 seconds, as you can see from here. However, if you want to sort using a CPU, which on this machine is an Intel 9th generation, well, it's a really nice generation, but the performance is definitely not that nice. And now it finished running this, and forget about the checking result because this part of code is broken. But trust me, I'm really running the quick sort code, and the quick sort code does give you the right result. So what it tells you is that for this program, right now we spend most of the time on a quick sort function, try to sort those numbers. So it takes 28 seconds, and 3.4 seconds is on the file input. So from MLOSLO's perspective, definitely we want to optimize the CPU execution time on the sort. So then we figure out that we can probably use GPU to run these pieces of a code. So now I have this version of the code that I use the Platonic sort that previously we have the demo to perform the sorting, and we will be using this 2080. So now I'm running this program, and again, to set up a fair comparison, I clear the cache, and it's the same hard disk drive. So the file input still takes 3.4 seconds. It's about the same because that part is optimized, is unchanged, right? But right now with the GPU sorting, right, it's only 9 seconds. And if I ran the program again, and if I perform sorting on the GPU, I hope the GPU get speed up a little bit, but it's also take about 8.8 seconds. So that's probably why I want to get the 8 on this machine. So, but for this one, right, you can see that with GPU speed up, right, that the sorting function becomes less significant, right? So now with the next generation of the GPU, I hope I didn't do the wrong thing, but looks like I did. For some reason, I thought I put the file here, right? Okay, so presumably, right? Presumably, if you use the CPU to run the program, then the sorting function would take the most significant amount of time. However, with the GPU, the sorting function may not be that significant, right? And if you choose the right algorithm, sorting function am I using here? And not confident yet. With GPU running the sort, you can see that the execution time gets significantly improved. And now, if I do this, well, if I have a better implemented sorting function, right, there are chances that we can get the sorting execution time a lot faster. So, well, you can see that, well, with GPUs, you can gradually improve the sorting function and make it better. And now, if you look at the timing breakdown, then definitely the file input, the 3.4 becomes more significant. So another thing that you could potentially do is that, well, let's try to use a better thing to execute the program that means you could use an SSD to execute it. And with an SSD, right, then definitely what you will see is we also reduce the file input to be only 0.24 times, right? And 24 seconds, right? However, previously, if your GPU sorting function only takes about 0.02 times, and you ignore the fact that file input takes the most amount of time, you are going to miss the opportunity of optimizing your program. So that's what this demo is going to tell you, is that the optimization is a moving target. So with different configurations, with different optimizations, and the most significant part could change, right? So when we are using a CPU plus a hard disk drive, then it turns out that sorting takes the most of the time. However, if you move the sort to the GPU, you can actually minimize the amount of time you spend on sorting. And turns out that the file IO, which remain unchanged from here, could become more significant. So then with GPU plus SSD, you can make a balanced execution time and making the total execution time better. So that's the sorting demo will try to tell you. All right. So yeah, so another lesson that you should learn is that with if we repeatedly optimizing our design based on MDOS law, then the most significant part will be changing. So it's a moving target. It's always important that you should revisit MDOS law every time when you apply some optimization. And another thing, which I think is perfectly reflecting to what you guys were mentioning, right? Sometimes people just tell you about a good thing about one thing, but they never tell you about the side effects. And this is something that MDOS law may sometimes missing. So saying that if a program spends 90% of time in A, 10% of the time in B, so according to MDOS law, we definitely agree that 90% is where we want to apply the optimization for. And well, today you have an optimization saying that, okay, it's really good. And I tell you that by using this, it can accelerate A by 9 times, but it would hurt B by 10 times, which they never tell you the side effect, right? And then you can, if you apply this to the original execution time format, you will see that, well, the new execution time, well, because this one, it has an overhead and you cannot apply MDOS law, so you cannot use MDOS law to count this. What you will see is that the new execution time would be the old execution time times 90%, because that's where we can start speed up, divided by 9, because we speed up by 9 times. And then the remaining 10% is actually slowing down by 10 times, so the time would be 10 times more. And if you added that up, what it actually leads to is that your new execution time will be 10% more than the new one. So you thought you are going to get significant speed up. However, in reality, you are recording 9% of the slowdown, right? So which is not what we are looking for. So these two things tells you that if there is a part of overhead or say side effect of a certain optimization, be careful, you may not be able to use MDOS law. And the other thing is that if there is something called slowdown, MDOS law is not some law that you can apply. So this is also a lesson that many of you already learned from the discussion that we had in the very beginning of the lecture, but also an example that we have here for MDOS law. All right. So another thing is that let's say those side effects aside, and that's assuming a perfect world where you have symmetric multi-core processor with n cores, a number of cores. And if you have a processor with no overhead in parallelizing your program, as long as you can find this F portion of program can be perfectly parallelized by using these n processors, you can imagine the parallelism would give you the speed up of 1 over 1 minus f parallelizable plus f parallelizable over n. But most of you know this is not a perfect world, so this never being true, right? But let's assume that we are living in such a world. And if we have a multi-core processors like that, how many of the following statements is or are correct? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I do see a lot of you have the same answer, but sometimes maybe this one or this two that you guys are thinking are different from this one or this two that other people are thinking. So why don't we still go ahead and do a quick group discussion? Maybe you will surprisingly find that, well, the two or the one that I'm thinking is different from your friends. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I'm inviting one of the group to share what your discussion landed and what are the well, so according to the result, looks like most of the groups think it's either 1 or 2, right? So shout it out, and if you think there's only one correct, that other people feel, well, this is my team and I'm proud of the one thing that I think you guys are wrong for the other thing, right? So feel free to share your thoughts with us. Any team would like to share? Should we give blue a chance? So in the blue team, I have Anthony, I have Chris, I have Hong Hao, I have Nathaniel, I have Simon, I have Tian Mei. Any of you would like to share? Anyone in the blue team? Okay, so quiet today. Okay, Samuel.
Okay, we didn't really come to a consensus whether it was 1 or 2, but our team pretty much agreed that 2, like statement number 2 and then statement number 4 were false.
Were false.
Yeah, but then we couldn't come to consensus about number 1 and 3.
But why do you think that's going to be false?
For number 2, because it's still bounded like how slow each single one is. I guess I don't know how to phrase it.
So how? Yeah, but how do you have a way to prove that? Do you guys ever thought about what's the way of proving it? You know, like when you answer a question in a midterm or whatever, right? If you don't have a proof, then it's hard to justify your answer. All right, Elliot.
I think I would say like you would try to prove it by like going to the extreme. So like if single core performance didn't matter at all, like if every single one of your cores was at like the lowest possible performance you could imagine, but you had like a million of them, I don't think you would still be able to accomplish useful tasks, right? Or is...
Okay, so David, you also have some idea.
Yeah. I was thinking like in terms of like thinking of like how like processes they might dependent on each other. Like so if you have like one result like that's like dependent on another, you have to do the first process first in like a core in like a processor, right? Suppose that if that processor is like really slow, then no matter how like good your synchronization.
Yeah, okay. So on this, right? So you are talking about like this one is not correct, right? But now, how about this one? Like, okay, so maybe I should ask the question, right? Can you easily use NDOSO to prove that any of this is correct or not correct? I'm asking for some formal improvement. Okay, probably not, right? So here's the thing, right? So let's try to review the NDOSO a little bit, right? So NDOSO is actually more than you can think, right? Remember, its format is 1/1 minus F plus F over S, right? It's F, right? So now, remember that with parallel, right, you can actually think about, okay, first of all, if I have unlimited parallelism, right, then presumably, right, I can remember that this is the number of parallel unit we have. So assuming there's no overhead, we are living in a great world, then the speed up you can get is actually unlimited, right? With unlimited, as what you are going to divide, right? Then this part can always be 0 as long as this part is some meaningful number, right? Which we have already said the slowdown is bounded, right? Even though each piece is slower, but if the slowdown is bounded, means that, well, even though this part is going to be slower, but given this part has unlimited, then this part would be essentially very close to 0. So your actual speed up that you can get is 1 over 1 minus F parallelizable, saying Fp, right? So the first statement is actually correct. As long as the slowdown is bounded, right? The slowdown itself doesn't affect the performance at all. If you have unlimited parallelism or your parallelism is in a very large number. So the first statement is actually correct. However, using the same formula, what's remaining here is 1 minus Fp, which is the part that you cannot parallel. So you cannot make it parallel. So what does that mean? Is that single core performance still matter because the 1 minus Fp is completely depending on single core performance. And 3, with unlimited amount of parallel hardware units, the maximum speed up will be bounded by the fraction of parallel parts. That is also true, right? Because 1 minus Fp, the larger the Fp, the better the speed up you can get. So that's determined by the fraction of Fp, the value of Fp. However, the last thing, as many of you learned, right, this is not going to be minor because it's going to add up at the end, right? So that's not, that's something that, and the synchronization data exchange overhead, that's not something that you can easily parallelize. And so it falls back again to the single core performance. So that's why this one, we got 2 statements that are correct. However, they are the first and the third. And that's where we are. And another example, which I already showed you in the very beginning of the quarter, is that we used to have the idea of merge sort. The complexity is lower, and Platonic sort that n log square n is lower. However, that's only on non-parallelizable hardware. And GPU is some kind of hardware that has thousands of threads. So you can imagine GPU is the case where the n of your m-DOS log could be really large when you apply the parallel execution. And another fact that you might be missing is that for m-DOS, for GPU, they have high bandwidth memory, which supports very fast data synchronization. So that part is also kind of like minimized in some sense. However, so with that, with respect to that, right, it's completely depending on how good your algorithm can parallelize your code. So if you use merge sort, yes, in the very beginning, if I compare numbers pair by pair, then turns out that I can have very high parallelism. However, the second time you try to do merge, the parallelism is shrink by half. And the later the stage, the parallelism is getting worse, right? So, however, for so turns out that in the very beginning, I do have very good parallelism, but at the very last stage, even though you are running the GPU, the code cannot be parallelized at all. So the performance is, so this kind of algorithm doesn't use the GPU very well. However, for Platonic sort, if you pay careful attention to the algorithm itself, in the very beginning, it has good pairs of parallelism like merge sort. And then in the second phase of the sort, it also has the same amount of parallelism. And then in every stage of its sorting process, they always have the same amount of parallelism. And so it always has the capability of using as many threads as possible on a GPU. So that's why this algorithm actually allow its performance to excel to surpass the traditional n-log-n algorithm, because the it better utilize the massive amount of parallelism all the time. So that gives you an idea that, well, although the algorithm itself take more steps, however, this is really the case where your parallelism does help you. So this question also reminds us two things, which is what I'm going to give you here. The corollary 3 is, if you can build a processor with unlimited parallelism, you don't need to take CS100 or CSE100 or 101 anymore, because algorithm doesn't matter. As long, it's more important that you teach other people how to parallelize your program, right? And Pythonic sort is one of the example, and another example is MapReduce. So MapReduce is also another framework. If you get a chance to look over it, it's also a programming model that encourages parallelism rather than encourages lower computational complexity. So that's also another case. And in MapReduce, they are not aiming at give you a set of very fast machines, and they are not aiming at even using GPU, this kind of very fast hardware, to speed up your program execution. Instead, each piece of program is running on relatively fair configured CPU-based hardware, but we have thousands of machines to execute your program. So that's why MapReduce becomes a model of massive parallelism. And data centers would like to use it for speed up their application instead of tweaking their applications for GPU. So that's another example of why modern system design would in favor a program that would be able to use more parallelism rather than very, very low complexity algorithm. So the future trend of software application design is for more parallelism rather than lower the computational complexity. So if you didn't do well in algorithm in CS105, you are good. You are good. You are okay, because you still have a future, right? Focus on parallel algorithm. All right, the fourth corollary that I want to say is that, well, looking at that, right, which is also another statement that you should learn from the question, is that single core performance still matters, because at the end, right, the 1 minus f part is going to dominate your performance. And if we cannot improve single core performance further, finding more parallelizable part, making this f parallelizable part bigger is more important. So it also falls back to one thing. The future of programming is about finding more parallelism. And computational complexity, again, it's only in a world where we dream, where each instruction takes exactly the same amount of time or the same amount of instructions to perform each operations. All right, and those are unlikely to be true. Okay, so this concludes our discussion on end-loss law. And now I'm going to tell you, how can we conduct fair comparisons, or how can we fool other people? So one of the examples that a lot of you would do is that, well, we have the experience that a lot of the game consoles, they would advertise their hardware capability with the with this matrix called T-flops, terafloating point operations per second. And here is the number that I can give you. So for PS4 Pro, the T-flops is about 4. Xbox One is about 6. Well, give you a reference, not saying that Switch can beat them. In fact, all of us agree that Switch is not their competitor. It's only 1, right? And GeForce GTX RTX 2080, which is exactly the same machine that I showed the demo, has 14 T-flops. But do you ever feel that running a game on your PC give you better result, better feeling, better experience than running a game on PS4 or Xbox One? Probably not, right? Why is that? So there must be something wrong behind teraflops. So now the question I want to ask you is that, under which of the following situation do you think T-flops could be useful? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, according to the discussion result, it seems like we definitely need some kind of discussion. So why don't you guys go ahead and discuss in group. And before that, don't forget to open the file that I send out to you. Now, let's go into the discussion room. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so Now I am inviting one of the group to share your thoughts with us. And it looks like even after discussion, well, our answers are kind of like diverse, right? So maybe yes, maybe no. Any group would like to share? Well, if not, that's random to pick a group. Okay, so, well, yellow. Anyone in yellow would like to share? Okay, Elliot.
Hey. So we were we discussed that like for it to be fair, then the two like programs should be sort of like comparable in terms of like what type of implementation they're using for their floating point numbers. So we didn't come to a lot of agreement, I think, but like at least I personally put one, and the one I think is correct is the compiler flags one, number 2, because it's the same program except it's just compiled in different ways, and so it's the most fair like comparison between the two. Whereas in the other ones, you usually have like some different implementation of floating point numbers between the two programs.
Okay, so can you elaborate more on the other 3? Like, why don't you think the other 3 are fair?
So for the first one, it says that it's using different types of floating point instructions, which frankly I'm not super familiar on the specifics of that, but it does seem like that would mean that there be a different number of floating point instructions, like for the T-flops formula, right? So it wouldn't be a super fair comparison, I guess.
Okay, how about the third one?
It's the same, like similar thing, like 70% of the time it's using floating point operations, and versus 90% of the time, then they would have a different number of instructions, maybe, possibly. And then the last one just seems like they're, because one of them's using doubles and one of them's using floats, right? So like the double seems like there would be more overhead, right?
Okay, so maybe, right, we can go back to the format of and thanks, Elliot. So maybe the best way to think about this question is that we should go back to, and I think I already gave you a very good hint here, right? So this is the formula of T-flops, right? And if you think about what the meaning in behind P-flops, you can expand this formula a little bit. The number of floating point instructions is actually the total instruction count times by the percentage of floating point instructions. And the execution time, again, instruction count times CPI times cycle time, right? And if you cancel those two things out, you will figure out that's give you the exact format of T-flops. And if we want to be a fair comparison, right, you should consider both IC, CPI, and CT. However, in T-flops, everything regarding the instruction count is ignored. So if we go back to look at that, right, first, one measure the T-flops with a processor with powerful floating point instructions. The other supports simple floating point operations. So the other one would have more floating point operations. However, that's not fair because it may have more execution time, but also a higher number of floating point operations, which potentially give you better T-flops, but turns out worse performance, right? So this is not correct. And the second one measures the T-flops with program compiled using optimization flags. And again, with optimization, you are going to change the instruction count, and T-flops doesn't consider instruction count. So to be honest, anything that contains instruction count is not something T-flops can fairly evaluate for you. And the other one major T-flops with 70% of floating point operation and the other was 90% of floating point operations. Again, the total instruction count is gone. So this is also not a fair one. And the last one, the work that you have to do with double precision and a single precision is also different. So the answer is actually A. Nothing could be fairly compared through T-flops in any of these cases. So T-flops is indeed not a very good, metrics. So one example that I can give you is that, well, you know, these days people talking about AI a lot, and here, right? NVIDIA tried to tell you how good the Tesla V100 is. So they tell you that with tensor cores, they can achieve 100 teraflops. So you think, wow, this 100 teraflops must be really good for everything that requires floating point operation. However, if you look at what they actually have this is that this 100 teraflops is only working on 16-bit floating point numbers because tensor cores only support 16-bit floating point numbers. And if you go back to single precision performance or double precision performance, it's actually only 7 or 14 teraflops. So if you imagine this tensor cores to help improving your gaming experience a lot, that's probably not the correct expectation. And another thing that people would say in machine learning is inferences per second, because they think, well, if that's set the teraflops aside, right? That's just consider the ability of delivering performance. Then what about inference per second, right? And again, for inference per second, right, it has a lot of missing point here is that what kind of machine learning model are you talking about, right? And because different machine learning model have different complexity, have different accuracy, right? Or what data set are you talking about, right? So it's really important that in the future that, well, and actually that's what people are doing right now is something called benchmark. We should define some kind of standard criteria, like everyone should run this model with what precision, deliver what kind of quality of result to make a fair comparison. But again, go back to the very fundamental performance equation. Even though none of the comparison will be fair if you don't include all the factors, instruction count, CPI, and cycle time into your formula. So the same thing, if you look at the inference per second, it's also something that's missing the instruction count as well. So that's also not a very fair metrics. And finally, because we are kind of like short on time, so I will do a quick demo and skip the reading the pop-up quiz question. So in the starting from the second lecture, I believe people start to have the confusion about latency and bandwidth, or say throughput. So let me give you there are lots of metrics about latency, also bandwidth. So if we think about the access time, the end-to-end latency of retrieving a data, that's access time. The end-to-end latency of submitting a command or starting a program till the end of the command or till the end of the program, that's called response time. So both of these are belonging to the type of metrics called latency. And the other one, the other type of metrics is called throughput, is the amount of work that could be done with a given time frame. So for example, bandwidth tell you how much amount of work that I can finish within a second. And IOPS, how many IO operations that I can finish within a second. T-flops, G-flops, floating point operations per second, inference per second, they are all throughput-oriented matrices. So there are many ways to improve throughput, and one of the best way is probably and one of the way is that you can just use faster hardware. So for example, these days, if we want to get better throughput in reading data, writing data, you definitely want a solid state drive. So if you have a SATA solid state drive, you can get up to 550 megabyte per second. And however, if you have a RAID, which each of the hard disk drive, it takes 10 milliseconds to retrieve your data. However, each of those would have a bandwidth of a 125. And if you aggregate it, then you can get an aggregated bandwidth that is around 4 times. If you have 4 disks, you can get like 4 times 125, right? That's also around 500 megabyte per second, right? So in fact, you can actually build a hardware-based storage system, give you the same amount of bandwidth as flash SSDs. However, is the performance really the case? So now, instead of asking you the question, I'm just going to show you that demo directly with a real machine that has both RAID and the SSD attached. So in this particular machine that I am using right now, I have a RAID like this. So this is a software RAID, and there's a tool called HDPalm in Linux that can tell you the performance of your storage device. So let me do a test on /MD0, which is the RAID device I have, and forget about the cache part because that's not real. However, if you just look at the disk read performance of that, right? So for this RAID, it's about 468 megabyte per second, right? That's really fast. And in the meantime, for this system, I also have a solid state drive attached to SATA that would give you about the same amount of performance. That is about 542, right? So this is actually a Samsung SSD. So you know that Samsung did not fool you with the number. They did achieve that amount of performance as we want to see. So now I'm going to show you a quick demo. It's on this machine. Sorry, versus CSE142 demo. It's the same GPU program that we were using and for the sorting example. But this time, when I run this program, I only have a very small set of data that I want to. I only want to sort 1,000 numbers instead of 134 million numbers. And the data, I would run this program for twice. For the first time, I would get the data from the local solid state drive. And the second time, I would get it from the RAID, which is this one. So now, let me run this program. So as you can see, right, with solid state drive, wait a moment, what's wrong with that? Am I getting it right? Okay, let me run this program again. Okay, interesting. The demo doesn't always give me. What if I make it smaller? Okay, so this is different from the last time I run it. Okay, I will check that, right? But the thing is that if you only fetch small amount of data, suppose the latency matters more than the throughput. And I don't know what's going on in this demo, but should I recompile the program? Okay, forget about that. No. All right, so the last time I ran a demo, I promise the number is different from what you see here. So maybe something in my configuration is wrong, but I will try to figure that out. But suppose, right, if you only fetch a small amount of data from the hard disk drive, you will suffer from the latency of accessing the data. So it should be 10 milliseconds always, even though at the end you got like 500 megabyte per second in bandwidth. And with a solid state drive, your latency is a lot shorter. However, and even though it takes more operations to fetch your data, it should still be faster. So that's why if you have a small amount of data to compare to fetch, suppose solid state drive still has its advantage. But for some reason, my demo doesn't work out today, so I will try to fix it and make it work the next time. So before you leave the classroom, several things I want to talk about. One, reading quiz due next Monday before the lecture. And the other thing is that please do read a book before and when you're doing the reading quiz. I saw some of the posts that you have on Piazza, but if you pay careful attention to the textbook, it's actually clearly state in the textbook that this is like that, right? So if you read the book carefully, you will figure that out. And don't just use your common sense to judge the answer of each reading quizzes. Otherwise, we shouldn't have a class here because being honest to you, CSE142 is not that intuitive as you can think. Assignment 1 due Sunday midnight and it's already available on our website. And some of you were saying about like, I cannot find a slide. I found 2 potential reasons because typically I would update my slides every time within an hour right after the lecture. So some of you post in the midnight saying that I didn't see it. I couldn't believe that. And there are 2 cases of that. First of all, you probably didn't refresh your browser. And sometimes if you go ahead from the Canvas does the cache. So it's not really updated every day. And another thing that I could think of is that we do have 2 columns of slides. And the second column, slide release, is actually the slide for every lecture. So if you are missing any slide, that's probably the right column that you should be looking for. And finally, some of our tutors from 142L is complaining that people were asking about the reading quiz questions about CSE 142. I just want to say, although I am the only step who is common between these 2 classes. But for the TA, he is only working for 142. And for the tutors, they are only working for 142L. So don't create confusion or don't increase their workload because they are not supposed to take care of the other side. And pay attention to the time that we allocated for different classes. And if it's not a 142L time, don't ask questions for 142L. And like this is 142 lecture, so we are not going to deal with anything regarding 142L here. And if you are interested about anything about 142L, it will start in about 40 minutes. Other than that, enjoy the rest of the day. I will see you later or next week.
続く